The minute we have a circuit diagram, we first need to take our colors and try to understand what the circuit is telling us. So from the negative terminal until a resistor, from the resistor through ammeters until I reach a resistor again, from the positive terminal until I reach a resistor again. What that clearly shows me is that this part over here is a parallel network and the 5 ohm resistor is in series. They've asked me immediately to close switch S, which is a good thing because I'd already gone over it with a line. And we notice that the voltmeter is 18 volts. So I'm going to write that in. There's only 1 voltmeter 1, so it's 18 volts. Oh, that's before. Then it asks you to calculate the total resistance of the external circuit. So let's start with 1 over R parallel is equal to, now I only put the parallel resistors into this, 1 over 6 plus 1 over 12, and I land up with 3 over 12, because I get a lowest common denominator. I notice that fractions aren't everybody's strong suit, so let's go slowly. Lowest common denominator of 12, 6 goes into 12 2 times, so I go 2 times 1, and I land up with 2 plus 12 goes into 12 1 times 1 is equal to 1. And then I land up with 3 over 12, but that's not the answer. I have to find what is the equivalent resistance of R parallel, and that is equal to 12 divided by 3, which turns out to be 4 ohms. So what I now know is that this system is 4 ohms. It has an equivalent resistance of 4 ohms. The total external resistance is going to be the parallel network plus the series resistor, which is equal to 5, and therefore I get 9 ohms. Calculate the reading on ammeter when the switch is closed. So if I need that, I am going to say, firstly, I know the external potential difference and I know the external resistance. So I can say that current is equal to potential difference external divided by resistance external, and I land up with 18 divided by 9, and I get exactly 2 amps. Now things start to get a little bit more interesting. Calculate the EMF of the battery if the internal resistance of each of the cells is 0,25. So there are 2 cells over there, so it's going to be 0,25 plus 0,25. So the total internal resistance is going to be 0,5 ohms. I know how much current is going through there because I've already worked out that this ammeter is reading 2 amps. So I know 2 amps is going to be going through the battery. If I now would like to calculate the lost volts, I can say V lost is equal to I, current, times the internal resistance. So that's going to be 2 times by 0,5, and it turns out to be 1 volt. If I've lost 1 volt and my original reading is 18 volts, my EMF is going to be equal to 18 plus 1, which is equal to 19 volts. It is the external voltage plus the potential difference or voltage that is used by the cells. There are other ways of doing it. I could have worked out the total resistance. So I could have said 0,5 ohms. Add that onto my 9 ohms. I get 9,5 ohms. Multiply 9,5 total resistance by total current. And I would have also landed up with 19 volts. Now I want to determine the heat dissipated. Heat dissipated is just another name for energy transferred. Another name for energy transferred is work done. So I'm going to look at all of my work done equations. I've been given a resistance 5 ohms. I've been given a time 2 minutes, which I'm going to change into 120 seconds. and I know that the current going through that 5 ohm resistor is 2 amps. So let us calculate that out, and I get work done is equal to I squared RT 2 squared 5 120, and that's 2,400 joules. And then if they ask me, determine when I open up the switch. So now I'm being asked to open the switch up. With that, it means I am cancelling this entire branch. It's gone. So I have a completely different circumstance. What stays the same? Firstly, EMF is constant. Doesn't matter what's happening, my EMF is going to remain 19 volts. So that doesn't change. My resistances stay the same. My total resistance doesn't, but each of the different resistances stays the same. So what's my total resistance now? My total resistance is 5 on the main branch, and I'm going to take 6 because now it's a series circuit off the main branch, so I just add them, 5 plus 6, and then I must not forget about my internal resistance of 0,5. So I'm going to say 5 plus 6 plus 0,5, and my total resistance is going to be 11,5 ohms. Now I can say current is equal to potential difference total divided by resistance total, 19 divided by 11,5, and I get 1,65 amps. What's interesting to note, or should be interesting to note for you, is that the current has come down. In other words, it has become more difficult. By removing one parallel branch, I have made it more difficult for the electrons to flow around.